Okay, we'll go ahead and get started on the next tutorial. Next speaker is myself. Give you a little background. I'm a senior HPC systems engineer in the technology integration group at the National Center for Computational Sciences at Oak Ridge National Lab. I started in HPC about 20 years ago at the Ohio Supercomputer Center before moving to the National Institute for Computational Sciences at the University of Tennessee to work on the Kraken project. And then from there, moved on to my current position at ORNL. For the past 10 years, I've been mainly focused on Lustre. Most of that background has been with Lustre system administration, but recently I've started cutting my teeth on some Lustre development. And today I will be talking about advanced Lustre layouts. So in this tutorial, I plan to cover several things. I'll start with a very short description of the normal Lustre file layouts. This is probably the layout that everybody is most familiar with and uses sort of day to day. And then I'll go on to talk about some of the more advanced features that have come out in recent versions of Lustre. I'll start with progressive file layouts, talk a little bit about data on MDT or DOM. Then we'll discuss file level redundancy or FLR, and time permitting, talk a little bit about self-extending layouts or SEL. Things I won't cover in this tutorial are directory striping, none of the D&E stuff here. This is just all going to be focused on files. And I'm also not going to go into details about how to choose file layouts to optimize I/O performance, since that will depend heavily on whatever application you're using. So normal file layouts, this is what everybody is most familiar with. In general, Lustre will take a file and we'll split it into chunks and distribute it over selected object storage targets in a round robin fashion. And for the most part, the splitting is mainly determined by two parameters that people tend to set, which is the stripe count and the stripe size. In this little diagram here, I've shown an example of a file that would have a stripe count of 3 and a stripe size of 1 megabyte. The stripe size simply determines how much data is written to a single OST before moving on to the second one, and the stripe count tells you how many total OSTs will be used to stripe your file. So in this case, an 8 megabyte file, the first megabyte will go on the first OST, then the next one goes on the second one. After you get to the third OST, it wraps around, and so that all the chunks of the file end up being distributed over the OSTs as shown here. Setting the file stripe parameters is controlled with the LFS get stripe command. One thing to keep in mind is that your files must not exist before running LFS set stripe, otherwise you will get an error. Once a file is created with a certain striping pattern set, it stays set, and you can't just change it by running another LFS set stripe command. You know, the common options that people would use for stripe count and stripe size. You'll see here in this example that matches the previous diagram. The dash lowercase c is for stripe count, dash capital S controls the stripe size. And those are by and large the most common parameters used. There are a few other striping options that some people may need in some cases. A common one that might be useful if you have different tiers of storage would be the dash P or dash dash pool option that lets you choose which specific OST pool your file resides in. Some other options that are much less frequently used would be dash I or dash dash index, let you choose the starting OST index for your striping. In general, this defaults to -1, which tells the Lustre file system to make a choice about where to start. And you can even specify dash O or dash dash OST if you want to list explicitly the OST indices to use. Again, these are ones that normally users probably shouldn't be using unless they know a lot about exactly what they're doing. Otherwise, you could end up creating a bunch of files on specific OSTs and end up filling them up. So to view file stripe parameters, that's simply done with the LFS get stripe command. And in this example here, I've shown what that output looks like for a file with, you'll see that in the output, there's the LMM stripe count, which is set to 3, and the stripe size, which is set to 1 meg. And at the bottom, you'll actually see all of the OSTs that are allocated to this file. They're listed in terms of their OST index number. So in this case, we had OSTs 2, 7, and 6 that were allocated to the stripe count 3 file. And you'll also notice that the LMM stripe offset matches the first OST index that was assigned to it. Now, progressive file layouts are probably one of the first big changes to the normal file layouts that people have been used to with Lustre. It's based on the concept of composite layouts. It gives you significantly more control over a file's layout. Normally, a layout will apply a single stripe count and a single stripe size to the entire file. But with PFL, you can actually use different of these standard or normal layouts on different parts of the same file. So you can think of it as sort of an array of normal layouts. And this can be used to potentially optimize I/O for files, specifically if they have non-uniform data structures in it. This diagram shows an example of how you might set up a PFL file, where you would have the first component covers the span from 0 to 2 megabytes, and you could set it up to have stripe count 1 with the stripe size at 1 megabyte. And then from 2 to 256 megs, your file might have a stripe count of 4 and a stripe size of 1 megabyte. And then for the remainder of the file, you increase the stripe count to 16 and maybe also increase the stripe size up to 4 megabytes too. PFLs are a good tool for Sys Admins as well, because they can help mitigate the possibility of a user filling up an OST. It's possible to find a default PFL layout that increases the stripe size as the file gets bigger. And so if you have users who never bother to change their file layout at all and use widely different file sizes, you could define a PFL layout that, starts out at stripe count 1 up to a certain small size limit, and then just gradually keeps increasing the stripe count. So whether someone writes, a 10K file or 2 terabyte file, you can have it striped at least somewhat appropriately. To create the PFL layouts, you still use the same LFS set stripe command as you do for normal layouts. The one thing you add is the -E or -- component and option. And that's used to denote the endpoints of the different components in the layout. So the general format will be LFS set stripe -E, and then you specify the endpoint of the first component, and then you give it the stripe options you want to use for that component, and then the endpoint of the second component with its stripe options, and so on, and then specifying the file name at the end. So in this example that would correspond to that previous diagram, you'll see that we have the first component -E at 2 megabytes, and we set the stripe count to 1 and a stripe size of 1 megabyte, and then we set the next component to end at 256 megabytes. And the last component that covers the remainder of the file, you can use -1 to specify the end of file, or you can also use just EOF to indicate the same thing. And the stripe options that you specify for each component should be all of the same sort of options that you can specify on a normal layout as well. One thing you do need to keep in mind, though, is that components need to be specified in order. This command assumes that the first component starts at an offset of 0, and then the next component starts where the previous component ends. If you were to try to rearrange these components and specify them in an alternate order, like in this example, you would just end up getting an error and it wouldn't work. As far as parameter inheritance goes, the first component in this layout will inherit its default values from the parent or root directory if you don't explicitly specify them for the component. And then later components will actually inherit their values from the previous component. So the example command that I show here would set up, the first component up to 2 megabytes, would set stripe count 1 and stripe size of 1 megabyte. Then for the next component, I have it end at 64 megabytes, and I override the stripe count and set it to 4. It would inherit the 1 meg stripe size from the previous component. And then the last component, I override the stripe size to be 4 megabyte, and its stripe count would remain 4 because it inherited it from the second component. One of the nice things about PFL is that it supports lazy initialization. Typically, when you set up a file, Lustre will allocate the OSTs it needs for it on a normal layout. For PFL, Lustre will allocate OSTs for the first component, but it only allocates OSTs for the other components when they're needed. So here's some output from the LFS get stripe where I used set up a PFL layout based on like the previous diagram. And I was going to go over some of the fields here that you might see. You notice in the red, you'll see the LCM entry count. That's telling you how many components are in the file. And then after that, you start getting blocks for each component. The yellow ones show sort of the component level fields where you'll see the LCME ID that indicates that this is a component with ID 1. And then you can also see the various flags that are set for the component. In this case, the init flag is set showing that it's been initialized. You'll see the start and end points for the extent, so you know what section of the file that component covers. And then the fields labeled in green, this block actually is then showing this striping details for the component itself. So you see stripe count 1, stripe size 1 megabyte. And since it's the first component and it's been initialized, you'll also see the list of the OSTs that have been assigned to it. The remainder of that output, here showing the second and third components, you'll see that yellow again shows sort of the component information. It shows IDs 2 and 3. Again, you see the flags here are a bit different. They show 0 because these components have not been initialized. So this would be prior to writing any data to the file. And the start and end points for each of those different components are also shown there, as well as the stripe parameters for each component. So you can see the stripe count for the second component is stripe count 4, stripe size 1 megabyte. But because this component has not been initialized, you have no list of OSTs assigned to it, and the LMM stripe offset has been set to -1. And similarly, for the third component, it has not been initialized either. Now, when you write data to the file, it will cause components to be initialized on the fly as you write data into each of these components. So in this example, if I were to run, say, a dd command and write 4 megabytes into that file, it would write those first 2 megabytes to the first component. And then after that, it crosses that barrier. There'd be basically Lustre does an internal pause while it figures out which OSTs to allocate to the second component, and then the process continues writing. And this is just completely transparent to the user process. But in this case, after I did the write, here I've shown the LFS get stripe output just for that second component. And now you'll notice that the flags field has changed from 0 to init, showing that it's been initialized. And of course, it's also evidenced by the fact that now there are OST objects that have been assigned to it. So it's stripe count 4. So we see that there have been 4 OSTs, 7, 8, 12, and 1 have been assigned to this component. And then the remainder of that 4 megabytes gets written into this component. Once the OSTs have been allocated for a component, they will remain allocated. So like truncating a file down to 0 doesn't make it unallocate them. It won't sort of revert back to how it was in the beginning. Now, this kind of thing also lends itself to doing dynamic layout changes. With lazy initialization, only the first component is required or is only going to be instantiated. So it's really only the the only component that is required to be specified when the layout is set. You can actually just specify that first component, and then others can be added or even deleted dynamically using LFS set stripe. There are some caveats associated with this. For one thing, you can only delete components starting from the last one. PFL doesn't allow there to be holes in the layout. If you have a component that has data in it and you delete that component, that data will be lost. So be very careful when doing that. If there's data in there, you will not be prompted before it is deleted. You also cannot write past the end of the last component. So if you've only specified the first two and you start writing and you go beyond those, you will get an error if you try to write any further. And this example here kind of shows that process of dynamically adding components. We start by using LFS set stripe to create a component that goes from 0 to 2 megs with stripe count 1 on the file, and that's the only one that we initially set. And if we want to, we can begin writing some data into it. So if we put in a meg of data, it writes in, everything's fine. And then before we write any more data, we decide to throw in 2 more components. We have one that goes up to 10 megs, and then another one that covers the rest of the file, each with differing stripe counts. And from that point, then we could then go in and say, okay, well, now we're going to write 20 megs to it, and there's no problem at all with that. It fills up the first component, the second component, and writes into the third component. And as you can see, if you do ls-lh, it has the full 20 megs in it, and that data has been extended into the third component. If you want to delete a component, you would use LFS set stripe and then use the --component -del command and specify the component index, that field that I'd shown previously for each component that has its ID in it. That's the one you'll specify here so it knows which one to delete. So if we were to do that with our example file, we delete that last component. If we look at the size, we see that it has now been truncated down to 10 megabytes, which is the end of where the second component was. So it destroyed, when we delete that component, we destroyed half our data, you know, and what we're left with is just whatever remained in those first 2 components. And at this point, if we then try to say write another 20 megs into it, we're now going to be writing past the end of that second component. And you'll notice here that we now get an error. It will write up to 10 megs and then proceed to give us an error. It says no data available. It's really meaning that there's no layout available past that to do any more writing to. One thing to keep in mind, though, particularly when specifying these component indexes, is that they are not necessarily sequential. The LCME ID field for each component is tied to the layout generation field that gets incremented every time there's a change to the layout. So if you say add 3 components and then you delete 2 of them and then you add some more, the second component in your file won't necessarily have a component index of 2. In this case, the third component had an index of 3 because we just created them one right after the other. So always be sure to check that field, looking at the output of LFS get stripe before you attempt to delete a component to make sure that you're deleting the correct one. There's a few other useful commands related to PFL. You know, with LFS get stripe, you can actually specify some options that will retrieve information just for single components. You can use --component count to list the number of components in the file. If you want to list information about a specific component, you can do so with --I and then the component index. You could also list components that only have a specific field. For example, if you use --component flag equals init, you would list only the initialized components on that file. One thing I should point out is it appears there's a slight mistake in the online manual. It shows that if you use --I without any number after it, it will list all the indices of all the components in the file. In my testing, it only actually listed the index of the last initialized component. And you also want to make sure that there's no space between the -I and the component index, otherwise you will get an error. As I mentioned before, like once a striping pattern is set on a file, you can't change it with another LFS set stripe command, but it can be changed with the LFS migrate command. And this would be particularly useful if you say have a file that has a normal layout and you decide you'd be better off with some sort of PFL layout. You can switch between them. And this is an example of doing that, where I created a normal layout with stripe count 1 that covers the entire file, wrote a bit of data to it. And then I decided, no, I wanted to have a PFL layout. And so in this case, you just do LFS migrate, and then you do the -E endpoint, stripe options, you lay out all your components and give it the file name, and Lustre will then basically create a new layout and copy the data over to it. And so in that way, you can basically change the layout of your file. And it also works the other way. If you have a PFL file and you want to go back to normal layout, you can use the same command to do that. There is one important note about file appends, and that's basically that, like I said, components are not normally initialized until data is written to them, but file appends are an exception. If you create a PFL file without any data into it, you could do LFS get stripe, shows only first component initialized. You can even write a megabyte of data into it. That's only affects the first component, and get stripe will show that only the first component's initialized. But if you try to append a few bytes of data onto it and then do a get stripe, you'll see that all components, are initialized. And so this kind of thing could cause, depending on your layout, it could cause the later components to be initialized with a large number of OSTs when there's actually no data residing on them. The second advanced layout I like to talk about is the data on MDT or DOM. DOM layouts are intended to improve small I/O performance by placing all or part of a file on the MDT. It is a type of composite layout, and is actually just a special case of PFL where the first component resides on the MDT itself. That first component will always have a stripe count of 1 because it doesn't make much sense to stripe across multiple MDTs if you're trying to speed things up by accessing the MDT only once when you access the file itself. And that the MDT that the data is stored on will be on that same MDT that the inode for the file is too. So when you do an open on the file, that MDT you're accessing is also the one that contains the data for the first component. And while it's primarily intended for small file I/O, it is possible that DOM can have its uses even for larger files. For example, if you say had a structured file that began with a small header that described the layout of the rest of the file's data, there might be some benefit to using a DOM layout where that header itself resided on the MDT, because maybe that's going to be frequently referenced and that data is going to be read quite a bit. And then the rest of the data can be stored on OSTs after that. And this little diagram just kind of shows where you might have a file where the first megabyte resides on the MDT, and then after that you have a stripe count of 4 for the rest of the file that resides on OSTs. Creating a DOM layout is done pretty much in the same fashion as a PFL layout. The only real difference is that when for the first component, you specify the endpoint for it, and then instead of giving, like say, stripe count, stripe size, you do -L MDT, which says to use the MDT layout. That will put the first component on the MDT, and then after that, the subsequent components are specified just like other PFL layouts as well. And this is an example of the set stripe command that would be used to create a file that matches this diagram here, where that first megabyte resides on the MDT, and then the rest of the file has stripe count of 4 and a stripe size of 4 megabytes. You can also use the -- layout option instead of the -L2 if you'd like. Since a DOM layout is just a type of PFL layout, there's displayed almost identically. There's just a few key differences. Notice that the first thing is that the stripe size will always match the extent end. There's the first is always stripe count 1. The stripe size is covering that entire first component, so they'll always match. It will show in here a stripe count, and you notice in red it shows a stripe count of 0. I'm not entirely sure why that is. It would probably be more accurately 1. But yeah, it'll reside on exactly 1 MDT. And then the obvious thing that shows that this is a DOM file is if you look at the LMM pattern field, for normal layouts, that would typically be RAID 0. In this case, it would be MDT. It looks like we have a comment here. Andreas pointed out that there's since Lustre 213, if files are created with the O-append, they use a special MDD append layout to avoid the initialize all components options, and he is given the LU number corresponding to that. So if you're a system administrator, the whole DOM thing could potentially be a bit scary. The idea that you can start dumping data onto your MDT, and filling it up might make you lose sleep at night, but don't worry, there are some knobs that system administrators have control over that can, help mitigate some of this risk. The main one being that they can set the maximum size of those DOM components. So on the MDS server, you would run, if you wanted to set it temporarily, you could use the first command, lctl set param -n, or if you want persistent, you could use the -P option. But you could set a parameter called DOM_stripe size. Now this is set on a per MDT basis. So if you wanted to, you could actually set different values for different MDTs. Probably the more common scenario is just set the same DOM stripe size for all of your MDTs. There are some limitations on the DOM stripe size value. By default, it's going to be set to 1 megabyte. It cannot be any smaller than 64 kilobytes and no larger than 1 gigabyte. And it must be 64 kilobyte aligned. You'll find that if you try to set the DOM stripe size to a value below 64K, the command will not return an error. It will appear to have worked, but when you query the parameter, you'll just see that it's been set to its minimum value of 64K. But if you try to set it to a stripe size above 1 gigabyte, you will receive a numerical result out of range error, and the value will remain unchanged. Likewise, if you try to set it to a value that's not 64K aligned, it basically just silently sort of rounds it down to the nearest 64K aligned value, and it will use that as the value. And so with this field, you can it doesn't control the total amount of data put on the MDT, but you can control how much of each file is placed on there to mitigate that somewhat. So someone doesn't try to turn around and say, well, let me just throw my entire 10 gig file onto the MDT so I'll have faster access to it. If you really don't want users putting data on the MDT, of course, you can just disable it completely by setting the DOM stripe size to 0, and then users will not be allowed to create DOM components on there any longer. If you had it enabled and then you disabled it, the couple things you should keep in mind are that if there are existing files with DOM components, those will remain unchanged. So accessing those existing files, they'll still be able to have that data on the MDT. Also, if a directory has a default layout defined on it that contains a DOM component, new files in that directory can still be created with DOM components. And if you ever need to track down, say, someone that might be abusing DOM and creating a bunch of data on it, you can do that with the LFS find command. If you use the -L MDT option, you can locate those files. If DOM is disabled and you attempt to create a DOM file, you should note that it will not fail. The layout just gets automatically altered. In this case, trying to create one here, you'll notice that I tried to put a megabyte on the MDT and then create a stripe count 2 for the rest of it. And since DOM was disabled, it basically just ignored that and it started the file, at 0 until the end of the file. It's all just stripe count 2 the whole way. The next topic I'd like to talk about is file level redundancy. File level redundancy, or FLR, allows users to define one or more mirrors for a file to provide extra data protection. So when you write to a mirrored file, only one of those mirrors is actually updated and the other mirrors are marked as stale and need to be resynced. This is referred to as the FLR delayed write implementation of that. But all mirrors can be used for reading data as long as they are not stale, and that can be used to improve read performance for files that are accessed by many processes in parallel. To create an FLR layout, this is the one layout that doesn't use LFS set stripe to create it. Instead, there's a LFS mirror command, and you use LFS mirror create -N, and then you specify the number of mirrors that use the layout parameters that follow it. So you say -N, a number, your stripe options for that mirror, as well as some flags potentially, and then that can be repeated for multiple potential mirrors for the file. The mirrors can be either normal layouts, composite layouts, or a mixture of both. For this example here, it shows a case where I start by creating 2 mirrors that have the same sort of normal layout of stripe count 2. And then there's a third mirror that's created that uses a PFL layout that has stripe count 1 for the first 10 megs and stripe count 4 for the remainder of the file. This also shows use of the --flags field. Right now, the only option that is supported is the prefer value, and that basically gives Lustre a hint about which mirrors it should try to use for I/O. But that is no guarantee that Lustre will use that. It's just more of a hint. There's a question in chat about in which version did LFS mirror appear? I'm afraid I don't know the answer to that. I'll have to look that up and post the answer in chat. I don't remember where that first appeared at. Now, displaying LFR layouts, this does use a standard LFS get stripe command. And this example here, I'll illustrate some of the fields that you would expect to see in that output. In yellow, you'll notice sort of the overall fields where it will list the mirror count. For the previous example, there were 3 mirrors defined, so I set to 3. The LCM entry count is 4, and that's because the first 2 mirrors were normal layouts, so they only sort of had that one component, and the last one was a PFL layout that had 2 components. So from Lustre's point of view, there's 4 total components as part of this file. One thing I should point out too is that just for the sake of brevity and being able to fit on this on the slides, I've deleted some of the not so important fields that would come from LFS get stripe. So this is not an actual full output from LFS get stripe. I've just tried to include some of the most important pieces. The first 2 components here, you'll notice that these are, you'll see that there's an LCME mirror ID field that is used to keep track of which mirror the component is part of. So in this case, I had set up originally, I had the first two mirrors were sort of normal layouts with a stripe count of 2. And so we have them here with mirror IDs 1 and 2. You'll notice that the flags are set, they've both been initialized. So they're normal layouts, and the prefer flag had been set on them. So that shows up at the LCME flags. Both of them have the start and end points cover the entire file. So they are from 0 to end of file, and they both have a stripe count of 2. So otherwise, they're basically the same, except they have different mirror IDs, and of course, they have different OST indexes associated that have been allocated to those mirrors. And then the remaining 2 components that are displayed from getStripe refer to the third mirror. So these are the PFL components for that third mirror. Here you see that they both these components have the same mirror ID 3 because they're both parts of the same mirror. And then the other parts look very much like your standard PFL layout. The first component has flags of init because it's the only initialized component, whereas the second component has its flag set to 0 because it hasn't had any data written into it yet. And then the start and end points for the extents are set to the corresponding PFL components. Now, when writing data, you'll notice that the LCME flags fields for some components may change to indicate that they are out of sync. As I mentioned earlier, when you write, we'll only write to one of the mirrors, and the others will be marked stale. So in this example, you might see flags might be set to init and prefer, and then when data is written to it, you might change to init, stale, and prefer. So that would be the case for my previous example. We had the first 2 mirrors had the prefer flag set to it, but only one of them can be written to. So when I wrote data to the file, one of those mirrors had its flags changed, and it now contains stale to let you know that that data was out of sync. And that's simply fixed by running the LFS mirror resync command on the file. It will go and it will resync up all that data. And if you're ever unsure if everything is up to date, you can always use the LFS mirror verify command, and that will check the consistency of your FLR file. Now, you can extend a mirrored file by adding additional mirrors to it, and that's done with the LFS mirror extend command. If a file is not already a mirrored file, it will convert it to be one. Any existing data in there is copied to the new mirror. And the syntax for it is similar to creating a mirror. You just specify the number of mirrors you want to create as well as the options for it, and those will be sort of appended onto the existing file. You can even take an existing file and add it as a mirror to another one. There's a special option. Instead of specifying stripe options, you can specify -f victim file, and it basically says, take this existing file and take its layout and treat it as a mirror of this. And so the victim file will basically disappear from the namespace, but all of its existing layout will be attached to the file as another mirror. The one thing you need to make sure of is that that the victim file contains the same data when you do that. By default, it will try to verify the data, and it will fail if it doesn't match. If you're sure that the file contains the same data, you can skip that verification step by adding a --no verify option to it. And then, of course, not only can you add to it, you can also split a mirror. If you have several mirrors into a file, if you want to, you can use LFS mirror split command, specify the mirror ID. If you want to give -f and the new file name, it will basically take that mirrored component and split it off as its own file and remove it from the current mirrored file. If you don't specify a file name with the -f, the default naming convention is to use the mirrored file name dot and then append the mirror ID to it. If you're just trying to get rid of a mirrored component without saving it into a a new file and you just want to just destroy it, blow it away, instead of -F, you can use -D or -- destroy, and it will just completely destroy the mirror. The last advanced layout I'd like to talk about is self-extending layouts. For self-extending layouts, this is just basically an extension to the PFL feature that allows the MDS to dynamically change the PFL layout if it detects OSTs that are running low on space. Normally PFL delays the instantiation of some components anyway. SEL splits these non-instantiated components into two parts. Basically, it creates an extendable component that is just a regular PFL component covering a part of the region, and the other half of that component then becomes what's called an extension component that's never instantiated and covers the remainder of the region. So when you do this, you're specifying, it looks like you're specifying a single component to PFL, and internally it's kind of splitting it into two components. And this diagram shows a bit of kind of what happens here. At the top here, you'll see, what would happen with, say, a PFL layout. The green sort of represents the data in the file. So if you imagine data fills up, and then we have a component that hasn't been written to yet that covers from 2 to 18 megs with a stripe count of 4. As soon as the data starts getting written to that field, Lustre allocates 4 OSTs to it here, and then starts filling those up with data. And so those 4 OSTs are used from the range of 2 to 18 megabytes, even if you haven't filled it up to 18 megabytes yet. Those are allocated for that entire range. With self-extending layouts, things operate a bit differently. That one component actually gets split. It starts out as, you think of it as a 0-length extendable component. And the rest of it is called the extension component. And it covers the 2 megs to 18 megs, and it contains, the stripe count of 4. It also contains an extension size, which tells it how much to incrementally extend the extendable component. So then as you write data into it, at first what it'll do is it will turn around, and as soon as you cross that 2 megabyte threshold, it will extend that initial 0-length component into a 4 megabyte length component. So now you've got that component covers from 2 megs to 6 megs, and then Lustre assigns 4 OSTs to it. You can start writing data into it. When you hit the 6 megabyte mark, Lustre will look and say, okay, out of those 4 OSTs that were assigned to it, are they still good? Do they still have plenty of space in it, or are any of them getting low? If they appear to be okay, it will go ahead and just sort of readjust that extendable component now to cover up to 10 megs. And then you can write data up to 10 megs. And then every time you cross that threshold, it keeps extending it by another 4 megs. And of course, as it keeps extending that initial extendable component, it also shrinks the corresponding extension component. So the sort of that blank space at the end gets smaller and smaller as it keeps expanding the initial component. And then eventually, once you hit up to the 18 megs, you would have the whole thing allocated, and that extension component just sort of disappears. Now, the real benefit of SEL comes from the policies assigned to it when OSTs start to fill up. The example I showed on the previous slide is what's called the extension policy. When all the OSTs in the current component are not low on space, it will just continue to use them. If they remain low on space the entire time, it will use those same OSTs for the entire component, and in the end, it will look no different than PFL when you're done. But things can change if some of those OSTs do run low on space. One of the extension policies called spillover is if the current component is not the last component and one of those OSTs runs low on space, what it will do is it will basically sort of stop using the current component early. It will just sort of cut it off, and it will start using the next component sooner than it normally would have. If the current component is the last component, then there's kind of two possibilities that can occur after that. One is called the repeating policy, in which case what it will do is if it sees an OST running low on space, it will create a new component that has the same layout as the current component, but it will pick different OSTs for it. In the worst case scenario, you may find that the current component is the last component. It's running, some of those OSTs are running low on space, but any attempts to repeat the layout and find OSTs that have more space available, those also fail. Like everything's running low on space. So in that case, it will just give up and say, okay, we might as well just keep using our current OSTs, and it will sort of force the extension of it. And this is a diagram showing of what the spillover policy would kind of look like if you started with a component, and then you, in this case, component 2 is the self-extending layout component, where it's incremented in 4 megabyte sizes. So it goes, first it gets extended from, it starts at 2, it gets extended to 6, and then 10. But then if let's say OST 3 starts to fill up, what it will do is that if the 10 megabytes, previously component 3 didn't start till 18 megabytes, it will basically get rid of that extension component and drop component 3 back down, and it will start at 10 megabytes instead. For the repeating policy, that takes effect when your self-extending layout component is the last one in there. And so this is a case where you're sort of extending it in 4 megabyte chunks, and then say one of those OSTs fills up. So what it does is it says, okay, well, still going to be a stripe count 4, but now I'm going to create a component, a new stripe count 4 component, and I'm going to pick 4 different OSTs for it. And then you can start writing there, and it will get extended in 4 megabyte chunks. And then say one of those OSTs fills up. Okay, well, I'm going to create another stripe count 4 component and pick 4 different OSTs, and I'll keep extending that in 4 megabyte chunks and filling it up. So this can allow you to sort of keep that same stripe count 4 layout, but it will dynamically adjust the OSTs that are allocated to it if any of them begin to fill up. And creating a self-extending layout is really the same as for a PFL command. We use a set stripe, but the one thing you add to it is this -z or -- extension size option that tells it how much to extend that extendable component each time when it hits the end of it. So in this case, I create a file where first component ends at 1 gigabyte, and I set the extendable amount to be 64 megabytes and stripe count 1. So it would be that first component would keep getting extended in 64 meg chunks until it hits the end at 1 gigabyte. Based on my testing, it looks like the minimum value for the extension size is 64 megabytes, although I'm not clear why that's the case. It doesn't appear to be documented in the Lustre manual. As far as viewing the self-extending layouts, I won't go over a lot of that here. You use LFS get stripe again, and as you'll see, the various components, the start and ends. The thing you'll notice is basically that when you specify it, what looks like one component actually gets split into 2 components here, and the extension component has this extension flag set on it. So in this case, you basically have a component starts at 0. It goes up to 64 megabytes initially, and then the extension component covers 64 megabytes up to 1 gigabyte. And then as data gets written to the file, this first component's endpoint keeps increasing upward, and the start component for the extension keeps going upward as well and shrinking, so that the sum of the 2 basically cover the same field. And in this case, this shows an example of where the extendable layout has not had any data written into it, and you see that first part of the component is a 0 length extendable component, and the extension covers the rest of it. So that was all I had for the advanced layouts. I'd like to acknowledge the Oak Ridge Leadership Computing Facility for the use of their resources, and then I'd be happy to answer any questions. Which looks like there are possibly a couple in this slide. There was a question about which version LFS mirror appeared. It was mentioned that it was added in 2.12. Nathan asks, in order to use LFS mirror to improve read performance for multiple clients, are any additional steps needed to ensure client reads are balanced across OSTs used for the mirrors? That I'm not sure about. don't know that there's any way to have the client, guaranteed to be used a specific mirror. I think that's determined by Lustre. I might have to check into that and put an answer into the chat. Alex asks, how advanced file layouts play together with overstriped OSTs? Can I specify to use OSTs on the same physical device for advanced file layouts? Yeah, so yeah, I'm not, I have not actually played around with the overstriped OST feature, but one thing you may need to take into account, specifically for FLR, if you want the added redundancy to protect your file, when you specify the different mirrors, by default, you can specify different stripe counts and things like that, but Lustre will not go through any special steps to ensure that those OSTs reside on, say, different physical servers or anything like that. If you want to make sure that you sort of have your file protected across like failure domains, you may need to do something like, say, set up an OST pool that contains the OSTs in rack 1 and then another one for the OSTs in rack 2. And then when you used FLR and you created those mirrors, in the first mirror, you could say create it in pool rack 1, and the next mirror is created in pool rack 2. And then that would force the file to basically get spread across, say, physical racks or whatever sort of failure domains you have for your file system like that. Otherwise, Lustre, won't inherently do something like that. So it's possible that you could end up with, mirrors having parts of their file on the same OSTs in most cases. So I asked, how to find out if all files of a file system are mirrored as expected. That's a good point. The only way I know of to ensure that is to do a verify on the file. But you could also, one thing you could potentially do is you could try to do like an LFS find and search for any file flags that would, I guess, have a stale flag set to it. That would be an indication that they're somehow out of sync and not mirrored. So that, I guess, that would be one way of checking it. But if you want to be absolutely certain that the data is mirrored as expected, I think the only way to do that is with a LFS mirror verify command. Okay, I'm not seeing any other questions come in, so thank you all for your time, and the next tutorial will start in about 5 minutes.